Okay, welcome everyone to this session of the first demonstration on the synopsys tools. So in this meeting, we are essentially going to learn about the various ways by which we are going to have the TCAD simulation of the nanotechnology devices which we use for our circuit designs. Okay, so Dr. Ramakant Yadav, he has agreed to give this demonstration, and you can ask whatever questions you want to him, and he is kind of an expert. He has recently finished off his PhD from our department, and it's my pleasure to have Ramakant with us. Thank you, Ramakant. So this session is getting recorded. Over to you. Thank you.
Okay, thank you, sir, for introducing me. So, am I audible, students?
Yes,
Yes, sir.
Yes, sir.
Okay, so all of you, yes. Okay, fine. So all of you first log into this IP 172.16.102.243. So all of you try this node 243. So today I will be discussing that how to design the various device structures using the synopsys TCAD tool. Okay, so first I will be starting with the PN junction diode. That is the simplest device that we can design in this tool. Okay, then we will go for MOSFET. Then beyond MOSFET, that work is the research work that we are doing in our department is the tunnel FET. Okay, so all of you create a new folder on the desktop. Okay, give the folder name. You can give any name, but I am giving demo. So first create a new folder on the desktop. Okay, and give the folder name demo. Okay, now inside this folder, okay, right click. Yes.
Sir, it is asking for passwords.
So you do not have the remote ID and password?
Yes, sir, I have, but it is displaying that
Okay.
it is displaying
I'll
your
tell
name.
you one thing. Excuse me. Hello. This is
Yes,
for all
yes,
the
sir.
students. These password issues have to be resolved separately. You have to speak to Mr. Rajshekhar Butla Rajshekhar, or Mr. Satish for those things. Okay, so don't keep on asking with this. So those of you who have already got working username password for the servers, they can do it. Otherwise, this session is getting recorded, so I'll be sharing with this recording on the Google Classroom anyways. So you just go through it, notice it. You can so that later on, when you have the username password, you can follow the tutorial as Dr. Ramakant is showing you, so that you can proceed further. Okay, because setting a password is not the responsibility of Ramakant sir. Okay.
So how many of you have the ID and password? You can raise your hands. How many of you have the? Okay, good.
Very good. So those of you who have got access to the servers, you can do it side by side. Those who have not, you can do it within a couple of days. And after this issue is resolved, then you can essentially log in into the server and go through the video recording as you can see right now. Okay. Yeah. Ramakant, so please proceed.
Okay, fine. So now in this folder, open the terminal. Okay. So here, so basically there are three sections of this simulator. Okay. So in the first part, we will be designing the device structure. Okay. So that is the CentOS editor. Okay. So if you want to open the CentOS editor, you can use this command. All of you write the command in the terminal and press enter. So this is the CentOS editor window. Okay. So here in this window, you can design 2D or 3D structures. Okay, so as you know that the PN junction diode, MOSFET or tunnel FETs all are 2D devices. Okay, so in this session we will be dealing with 2D devices. So you can minimize this. Okay, just minimize this. So first, what you have to do, go to the view. Okay, GUI mode. Okay, so by default here 3D is selected. Okay, so select 2D here, and the CentOS will be designing the 3D device. Okay, so what what will be the width? So by default, the CentOS will consider the width of the device because we will be designing 2D devices. Okay, so the width of the device, that is W, will be 1 micrometer. By default, in the CentOS, it consider 1 micrometer width. Okay. Now 2D selected, then draw. Go to the draw. Okay, so here it is auto region naming. Okay, so deselect this, because whenever you are creating the different regions, okay, so we will be giving the different names. Okay, so if you don't deselect this, okay, it will create some random names, so you will not be knowing what are the names. So second thing is unselect this. Okay, so this is next. We will be designing the devices of different sizes. Okay, so you have to give the different dimensions of the device. So to check what will be the dimension of the device, select this. You can go to the here, draw exact coordinates. Okay, you can select it from here, or the right side. This is the icon, shortcut icon of the select exact coordinates. Okay, so whenever you are drawing a suppose rectangle, it display what are the coordinates of this rectangular window. Okay, so let us first draw the rectangular window. So here you can select the different materials. Okay, so different materials are available here. So by default, the silicon is selected and we want silicon only. Okay, so now select the type of the region that you want to create. So I want to create a rectangular region. So select this. Then create a region here. So here you can give the exact coordinates. So let us give x first vertex 0 and 0. Here I want to create a rectangular region of 90 nanometer length. So this is 0.090. Then let us take the thickness. Okay, thickness of the device, that is how much we can take any. So let us take 30 nanometer. So I have given the coordinates 0, 0. So here the entries are in the 0.09 and 0.03. Okay. Give the region. So you can give any region. Let us give region, or let us give this is n region. So here you have the different x-axis and y-axis. So if you want x-axis horizontal and vertical y-axis, you can select this. Okay, if you select this, it is like this. Okay, so this is x-axis and this is y-axis. You can move this region here at the center. Okay, now you can display the grid so that you can understand that what is the region. So this is the shortcut icon of the grid. Okay, and let us give the grid region is 3 nanometer. Of each grid is 3 nanometer. Apply. So you can see this. Now all of you have done till this. Yes, if you have done it. Students completed? Unmute your microphones and say yes, no, or chat box. You can type it in the chat box if you have done it. How many of you have done it till this?
Sir, we'll do it later, sir. Like that ID, we didn't get exactly, sir. That SCD something.
Sir, excuse me, Ramakant.
Yes, sir.
Yeah. Suggest is you just show one after another slowly. Okay. Do not ask for the do not wait for the students to complete. Otherwise, many of the students are working from home actually. Okay. They are not on
Okay.
campus, so if they are doing a remote login and doing it, it is going to be very slow for them. Anyway, this is getting right. So I will share the videos. They can check it later. Okay. Rather, what I request you to do is, now you are probably showing the diodes, right? Later on, you can do for the MOSFET, MOSFET, and the so basically,
No,
this
I will do it for TFET and then MOSFET. Then finally, I will show the final structure that we have done in our research for TFET.
yes, whatever.
Yes.
Okay. Are you doing a diode now? No.
No, I am doing diode only.
You are doing diode, right? After
Yes,
diode,
sir.
you will do what? TFET or MOSFET?
MOSFET. I will
MOSFET.
design the MOSFET here, but for TFET, whatever structures we have.
Yeah. No need to show the design
I
for
will
the
show it
TFET.
and show the
Yes.
IDVDS.
What else? You do from scratch the diode. You do from scratch the MOSFET. You can do
Yes,
from
yes.
scratch the MOS capacitor also. Okay.
MOS capacitor I have not tried, sir, but MOSFET and
Oh,
diode.
MOSFET also. You do it from scratch so that the students will understand.
MOSFET and diode I will do it from the scratch.
Yeah. And do it recording. No need to keep asking whether the students are doing it also. Okay, because many of them may not be at the same page as you are. Okay. Yeah.
So students, whenever you have the doubts, you can just unmute your microphone and stop me. Okay, I will be continuing from here. So we have created the N region. Okay, so in the diode we have two regions, P region and N region. So let's create the P region inside this. Okay, so now select this snap to grid. Okay, so select this snap to grid. Select the region. So sorry, select this rectangular region. Now you can create this. So the entire region, okay, the length of the entire region is 90 nanometer. So I will create a P region of 45 nanometer. So you can just change the here 45. Okay. Let me just do it again. Okay. So 45. Give the region name. So this is P region. Okay. So two regions, both the regions are created, N region and P region. Okay, so after creating the regions, we have to do the dopings in the N region, N type. We have to make the dopants, N type dopants and P type dopants. So for doping, go to the device. So here you select the constant profile placement. Okay, now here you will see placement type. Okay, so in the placement type, select the region. So there are two regions. So you can see here there are two regions. So if you select P region, the P region will be highlighted here. If you select N region, the N region will be highlighted. Okay. Now let us dope the N region with the P type of N type of dopant. So let us give the name of this. We can give N region. Here also you can give the same name. So this is N type. So we have to dope with phosphorus impurity atoms. Okay. So let us assume the doping is 1p 10 to the power 20 per centimeter cube. Then add placement. So N region doping we have done. Now if you want to, now we have to do the doping in the P region. So select the P region here. Okay, now this region is selected. Change the name here. So change the name also, P here and P region here. So this is P type. So we can select the boron active concentration, and let us give this is 10 to the power 90. Now to cross check this, okay, you can just see here. If the P region is selected here on the top of this window, you can see this is the P region and the doping concentration is 1E10 to the power 19 per centimeter cube. You select N region from here, you will get the phosphorus dopants, and the concentration is 1E10 to the power 20. Close this. Okay. Now after this, what will be the next step? So this is my N region and this is P region. Okay, so create the contacts. Okay, so to create the contacts, first you have to set the contacts. Okay, so this is N contact. So N contact, set it. Okay, we need two contacts. Okay, P contacts. P contacts. You can change the color of this. Let us give some different color. This is P. Okay. Now, before making the contacts, let us again check which one is N region and P region. So N region is this. Okay. Right side is the N region and left side is the P region. Okay. So again, go to the contacts, set contacts. Okay. Now make the contacts. So first select the N contact. Okay. Activate this. Okay, and first you have to activate the N contact. Okay, then here, because we have to create the contact at the edge. Okay, at the edge. So select the type of this. So this is S. Okay, take the arrow and click here. So this S is selected. Okay, now after selecting this, go to the contacts and set contact. So you can see this is the N region contact. Okay, N contacts. Similarly, for P contact, first you activate the contact, okay, then select the P contact as, go to the set contacts. It is created P, okay, so both the contacts are created. So let me just summarize this, what we have done. First, we have created a silicon of 90 nanometer, okay, in the silicon we have created the N region and P region of 45 nanometers, okay, then we have done the doping of N type and P types in the N region and P region. Next, we have created the contacts on the N side and P side. Okay. Now, this is the device structure. Okay. Now, this device structure we have to simulate if we want to see the current characteristics. Okay. So, we have to apply the voltages and calculate the current at the different points. So for that, first we want to create the mesh. Okay, so define the window, type of the window for the mesh. So let us take the rectangular window. So using this rectangular window, select the entire device. So this entire device is selected. Okay, now I have to create the mesh. So go to the mesh again, refine placement. Okay, so in the refined placement, this window is selected. Okay, you can give the name of this because we have only one window here, so I am not changing the name. Now the minimum size of the mesh, you can create the coarse mesh or fine mesh. Okay, so if you are creating a fine mesh, it will be calculating the ID current at each node of the mesh, so it will take more time to simulate this. So I'm not creating very fine mesh, so I'm taking 3 nanometers in the x direction. This is 0.03 nanometer maximum size. Minimum size I am using 1e and to 1e minus 6. So 1e minus 6. Okay, create refinement, close this. Okay, so you have created the mesh. Okay, so next is you have to build this mesh. So build this mesh and make sure that mesh viewer. So after build is done, it will open a S visual. So if this is selected and build this device structure will be open in the S visual. So this is the S visual. Okay, So you can see here, this is my N region and this is the P region. Okay, this is the mass. You can see the mass. Okay, doping concentration also you can see. In the N region, we have 1 e 10 to the power 20, and here you have 1 e 10 to the power minus 9 per centimeter cube. Okay, so this is just for checking this. Now close this. Save this. Okay, you could have done it at the starting of this. Okay, so make sure you save this file also. So give the name of this file. So let us give any name, diode. Okay, you can create and you can run the mesh again, build the mesh again. Okay, so this is the device structure. Okay, this is the device structure. Now, to apply the different voltages, now what is this? This is N region, this is P region. So I have to, now if I want to see the current voltage characteristics, what I have to do? I have to apply the positive voltage here and zero voltage here and change the voltage from 0 to, because in the IDVGS, okay, the ID, okay, or the I, okay, the I current of the diode will be changing with the voltage. So I have to swap the voltage from 0 to 1. Okay, let us apply the 1 volt. So 0 to 1 and calculate the value of I for different values of this. Okay, so that is the second part of this. So for that we have the S device. Okay, so in the S device, so I have already shared the CMD files here. Okay, you just change the .txt file to CMD file. Okay, so now I will copy the CMD file, diode CMD file. So for diode, I am showing only the I and IDVGS characteristics. Okay, for MOSFET, I will show you the IDVGS and capacitance characteristics also. Okay, so here copy this file. Okay, open this file. So in this file there are different sections. Okay, so in the first section, so whenever you are building this mesh, okay, you just press F, the mesh.tdr file will be generated. So diode.tdr file, where is the diode.tdr file? Diode underscore mesh.tdr file. Okay, so this is the file that is having all the parameters of the device that we have created in this CentOS. Okay, so we have to read this file in this S device. So first I am reading this file using the grid diode underscore mesh.tdr file. So after simulation is over, it will create different files, plot files, current file, output file. So these are the different files will be created. Now we have the electrode, we have two contacts, N contact and P contact. Okay, so initially we are giving the voltage to both the contacts 0 and 0. Okay, and N contact will be always grounded and P contact voltage will be changing from 0 to 1 in a step size, in a step. Okay, so we will make the step size. You can change that step, for example, from 0 to 0 0.005, 0 0.001. Similarly, you will calculate at each step, you will calculate the value of I. Okay, so here, now this is the plot section. In the plot section, we are using different type of current and mobility equations. Okay, doping, type of dopants and the generation recombinations. Okay, if you want to go it detail, there is a detailed manual here of the CentOS, where it is. So this manual is given. Okay, so all these detail, the discussion of the detail, each command is given here. Okay, so you can check it in this CentOS user guide. Okay, if you want to go it in the detail, I am just giving the brief. Okay, then there is a physics section. In the physics sections, we are giving different type of, at what temperature you are simulating this device, then mobility, type of mobility, then recombinations, different type of. Then math sections, we are giving different electron reference. Okay, in the solve section, okay, what are the initial step size? Okay. Next is the gate voltage. So what is the final gate voltage? We have to swap the voltage from 0 to 1. Okay, so this is the goal. Okay, so I have started the gate voltage from 0 and it will simulate till 1 volt. So let us run this file. Okay, so again go to the terminal, open the new tab. Here you can type s device, okay, space the name of the cmd file. So the name of the cmd file is test_dc. So dc, just press enter. So you can see it is simulating. So bgs is increasing. So you can see here, I just show you. So okay, so N contact voltage is always 0. P contact, it is started from 5 into 10 to the power minus 2. Okay, so what are the current levels you can see here? Then it is increasing. The P contact value is increasing. So it is 1.1 into 10 to the power minus 2. That means 0.1 volt. Then it is increasing 0.19. So it is going at each value. You can calculate the electron currents, P contact, N contact, hole current, electron currents. Okay, so finally if you check, finally the N contact is 0, the P contact reaches, the P voltage reaches the goal. What was the goal? Goal is 1 volt. Okay, so these are the current values you can check. Now in the third section we want to plot this, okay, current versus voltage. So to that, what you have to do, you have to open this as visual and this, okay, as visual plot you have to open, as visual tool you have to open. So you just enter this command. So this is the as visual. Okay, so this, after this simulation is over, okay, the file name here I have given new current prefix. So this is the file name. So this is id_demo. Okay, then at the top of the current. Okay, so it will create the file name that you can see here. Open the file. So this is the file id_demo _diode. The current file name I have given current diode. Okay, so _design.plt. So design.plt file is having all the values. So I want to plot the P contact is the, so x-axis is the voltage and y-axis is the current. So P contact outer voltage on the x-axis, P contact total current. You can plot the electron current, hole current, but I am plotting the total current. So total current on the y-axis. So you can see this. So this is the IV characteristic plot for different values of BGS. Now if you want to see what is the values at different, you can just use this prof and check the values. So at 1 volt, you can change it here also. At 1 volt, the current is 486 microamperes. So you can check this. So 0.00 amperes per micrometer. Now that how to, now this is the plot. Okay, so how to get this data, IV characteristic data into CSV file. Okay, so for that you can go to the data. Okay, if you want to export the data into CSV file, go to the export. Okay, so there is only one plot. Okay, there is only one plot. If there are multiple plots, you select all the plots here. Okay, so you select all. So there is only one curve, so I am selecting only one. If there are multiple curves, you select all the curves in the here and take it to the right side. Okay, then export. Give the file name diode.csv. Save this. So you will see that diode.csv data is, sorry, this file. So this file is having the current values for different voltages. So this is the voltage changing from 0 to 1 in at the different step size. Okay, if you want a constant step size here, that one is also possible. You just uncomment this. You can remove this. It will create a. It will give the constant step size of 0 to 5. Okay, so here it is a random step size. So Vg is the voltage is increasing in the, is not increasing in the constant, but you can see this. Okay. So if there are multiple plots here, again I am just repeating, go to this. Okay. Select all the plots from the available curves, take it to the curve to export, then export the data. It will give all the data of all the plots into the CSV file. Now, any questions in the designing of the diode? Yes, students, any questions? Yes, if no questions, then I will go to the next device, that is the MOSFET. Understood, everybody?
Yes, sir.
Students, nobody is replying. If you have any questions, feel free to ask the doubts. No doubts? Okay. If no reply, then I will
Carry
end.
on. Ramakant,
Okay.
please carry on.
Okay. So this is the, now inside this I will create the another folder, that is NMOS. Okay. So again similar steps. Okay. So open the terminal, type this command in the terminal. Okay. Press enter. So let us close all the device structures. Okay. This I just close all the terminals. Okay. Then we will start. Okay. This one also I close. So next I have created a new folder, NMOS. Okay, inside this folder, open the terminal, type this command, enter. So again, minimize this so that you will get the more space for designing the device. Okay, so again, same steps. First, you have to select the 2D mode. Okay, draw, unselect the auto region. Okay, then select the exact coordinates. Okay, so we are designing the N MOSFET. Okay, so N MOSFET. So first we will create the substrate. Okay, so again select the rectangular. Okay, create a region here. So I am designing 180 nanometer, 180, not exactly 180. So 180 nanometer region. Okay, so this is 0. First coordinate is 0, 0. So 180 means 180 nanometer means this will be 0.180. Okay, so this is the length of the substrate. Okay, substrate. Then the thickness of the device, that let us use 45 nanometers. So this is 0.45. Let us give the name of this. This is P substrate. Okay. P substrate. Okay. So this is the P substrate. Okay. You can zoom it. fit to the window. Okay, and zoom it. You can zoom it and change it to the mid of the display window. Okay, now apply the grid. So apply the grid of 3 nanometer. Apply. So okay, this is very fine grid. So let me just change this to 5 nanometer. Okay. Now this is the substrate. Okay. So inside this substrate, I have to create the source and drain regions. Okay. So again, I create the source and drain region of 30 nanometer. So I just create source and drain region of 30 nanometer, and let us take some thickness of this. No, let me just, so before this you have to select this snip to grid. Okay, so this one I want 30, and let us take this is y. Sorry, let me just, okay. I just check. If you want to see the dimension, you can check it here. You select this vertex, and this is, so you can check it. This is how much? Oh, this is 450. Okay, this is, let us delete. I have made some mistake. Let us create again. Okay, so 0, x coordinate. I just give 180 nanometer. So 180. Okay, 45 nanometer. I think I made mistake here. I have written 0.45. So this is 0.045. Okay. So this is the substrate where it on. Okay. Now create the source and drain. Okay, so select this snip to grid rectangular. So I want this 30 nanometer, and the thickness of this source you can take. So this is 45. So let us take 20. Give the region. So this is source. Okay. Similarly, create the drain. So how many columns we are taking? 1, 2, 3, 4, 5, 6. 6. So 1, 2, 3, 4, 5, 6. Okay. So this is drain. Okay, and this is the substrate. Okay, so source, drain, and substrate. Okay, now what will be the next step? Doping profile. So this will be the p type. Okay, and source and drain will be n types. Okay, so let us make the dopings. So constant doping regions, first substrate. So you have to, so let us write the region name. So this is substrate. Okay, here also you can give the same name. So this is p type. So boron atoms. Okay, let us give this is 1 e 10 to the power 18 per centimeter cube. add the placement, then select the source. Okay, so source is n type. So this n type, that means phosphorus atoms. Let us give this is 1E20 and change the name here also. So this is source, source. Again, make sure that whenever you are selecting here, check it in the device also. The region corresponding to this will be highlighted here. Okay, and this is p type, so p type. Add the placement here. Next is the this one I have to change. So delete this again. So this is substrate, then source, change the names here. One E20, clear, add. Okay, select the drain region. Okay, give the name here, drain. Change the name here also. Let us take this is 10 to the power 19 per centimeter cube. And you can see the region, drain region is highlighted here. So add. Okay, now just to cross check. Okay, just to cross check, you can check again, change the regions here. This is substrate. So substrate region is selected and the doping is 1E10 to the power 18, but it is phosphorus. Okay, so let us change this to the boron. Okay, then select the source region, check the doping, phosphorus 1E20, clear, correct. Drain region, next is drain, phosphorus 1E90, substrate 1E18, clear. Okay, done. What is the next? Next step, we have not created the gate. Okay, so there will be a gate on this channel. So this is the channel region. Okay, so on the channel region there will be a gate. So we have to create the gate here. So gate is oxide. So you have to select the oxide here. Before making the doping also, you could have done the gate and oxide. Okay, you can do it after also. So I have selected the oxide material here. I am creating a 5 nanometer gate on the channel region. So this is the gate. You can give the name, that is gate oxide. This is the gate oxide. Okay. Now on this I can create a gate terminal. Okay, or the gate. So on the oxide you have to create the gate. So we will create a gate of polysilicon. So polysilicon, material of polysilicon, you can create a gate of 5 nanometer again on this. I think oxide we could have given. So this is gate 1. So this is gate. Okay, this is the oxide. We are using a single gate devices. If you want to use the double gate devices, double gate MOSFET, similarly you can create the oxide and gate on the back side of this device also. Okay, so now, so this is the complete device structure. Now we have to make the contacts. Okay, so to make the contacts, again set the contacts. So we need 3 contacts. Okay, so let us give first contact it the gate contact C, because gate name we have already given here. So you cannot give the same name to the contact name as the region name. Okay, so contact names should be different from the region name. Okay, so that's why I have written dash C. Okay, so this, sorry, set this. Okay, similarly you can give the source C and dash C, set. Then drain. You can change the color also if you want. So we have defined the 3 contacts. Okay, now we have to set these contacts. So first select the gate, activate this, change the body select type. So this is edge, and take the cursor from here, select it, set the contacts. So the gate contact is created. Similarly, take the source contact, activate, select this, set. Okay, drain, select the drain region. First activate this, select it is selected, set. So what will be the next step? Creating the mesh. Okay, so define the rectangular window. Let us first take a region that covers the entire device. Okay, so this is the, like, you can give region 1. Okay, define the mesh in this region. So this region is selected. Okay, so you can give the name here also if you want, region 1. Create the mesh. So let us take 0.003 nanometer mesh, maximum size. Minimum is 1e10 to the power minus 6. Similarly, 1e10 to the power minus 6. So I have created the 3 nanometer mesh for the entire device region. Okay, if you want to create a fine mesh in, because what is the main region? The main region is the channel region. Okay, carrier transport will be happening in this main region. Okay, so if you can create another mesh, fine mesh. Okay, so multiple meshes are possible. So let us take the another region that is having only the channel region. So this is the channel region. Okay, so I will create the region 2. Okay, so here you can create a fine mesh. Okay, so region 2. So region 1 is 3 nanometer. So let us take the fine a smaller mesh in this. So 2 nanometer. You can take 1 nanometer also. What will be the? It will take more time to complete the simulation. What the results will be more accurate. Okay, if you are, so you should take the minimum possible maximum size. Okay, so we have observed in our research that if you are taking a 1 nanometer mesh size, it is giving the best device characteristics. Okay, just to show, we are taking the 2 nanometer. Okay, you can check whenever you are designing the device, you can see the influence of the meshing size on the device performance. Okay, that is the optimization. That part is the optimization of the device, but we are not going in the optimization part. Okay, so next you can build the mesh. Again, before building the mesh, always save the mesh, save the device. Okay, so save nmos. Okay, now build the mesh. So you will see a message command, meshing successful. Okay, so if there is any problem in the device, okay, you will get that meshing is not successfully done. Okay, so if meshing is successful, this device will be created in this S visual. Interchange the axis. Okay, so this is X, so you can check. This is the back side. What we have drawn is interchanging that. Here, this is X and Y axis. Okay, so this type of device. So source, then gate, oxide, channel. Okay, if you want to see this, okay, so you can see this is the coarse mesh of 3 nanometer. But inside the channel region or in the channel region, in this region, this mesh is very fine mesh. Okay, so done. Now for IV characteristics and CV characteristics. So I have, there are 2 CMD files. Okay, there are 2 CMD files. One file is DC analysis and one file is for AC analysis. Okay. So so first the CMD file that I will discuss for the diode, that is for DC analysis. Okay, now I will be using the AC analysis file. So this is the AC analysis CMD file. I have uploaded both the files in the Google Classroom. Okay, so you can copy these two files in your remote system whenever you are doing this designing part. Okay, so NMOS, refresh this, Control B. Okay, so this is my device. This is a file mesh.tdr file that is having all the device parameters. Okay, so open this. Similar to this device, you can give some name here. And this is, you can give N MOSFET also. N MOSFET. Okay, or let it be saved. Any name you can give. Okay, what is important? Important to us is you have to read the mesh.tdr file here. Okay, so what was the name of the file? I have given NMOS, yes, NMOS. So here the NMOS TDR file. Now here we have three regions, three contacts. One is source, drain, and gate. So again you have to check the name of the contacts. What was the name we have given? Gate C. Okay, gate -C. Okay, so you have to change this C. I was using gate source 1. Use the same contact names created in the device in the CMD file also. Okay, so first source voltage is 0, drain voltage is also 0, and gate voltage is also 0. So here I will be plotting ID BGS characteristics. Okay, so ID BGS, that means I have to swap the gate voltage from 0 to 1 volt. Okay, so and drain will be 1 volt. So drain voltage also first. So first we will swap the drain voltage from 0 to 1 volt. Okay, first step. So drain will reach the goal 1 volt. Then we will swap the gate voltage from 0 to 1 volt. So you will get the ID BGS plot at the BDS is equal to 1 volt. Okay, so similar to the DC files, here we have plot section, then physics section here, math section. Here you have to extract the parameters from the device. So I have created a device and tfat underscore b7. Okay, so here that is the difference between the DC file and AC file. First few sections are same. So here I'm giving the terminal names. Okay, so drain C, I am giving D. Okay, this is the drain terminal. Similarly, source, for source, this is S, and for gate we have G. Okay, now if you are using a 4-terminal double MOSFET, okay, then there will be one extra terminal here. That one you have to take front gate and back gates. Okay, so you will get one more. So we are assigning the voltage here. Source voltage 0, 0, 0. Okay, so first you see here, first we are changing the voltage, drain voltage VG.DC to 1 volt. Okay, so BD will reach the 1 volt. Then next gate voltage, sorry, yes, so here BD.DC, so this is the drain voltage, it will reach the 1 volt here. So first drain will reach the 1 volt, then VG will start increasing. So finally BG.DC, okay, BG.DC we have defined here, BG.DC is equal to 0. So from 0 to 1 volt. Okay, so this, let us run this file. Open the terminal. So this is AC file. Small AC, okay. line number 69.
I guess we have to change the name. N MOSFET you have used and N TFET.
No, anti-fat V7. So anti-fat V7, source, drain. Let me just check. Oh, this is a typing mistake here. The source, right? Source is spelling, this is a spelling mistake. So same thing you have to take there also. So let me just copy this. Okay, you can make the changes later on. Okay. So I will be okay. Source is spelling is not correct. Okay, you can just change this. Or I can make the changes in the device also. Let me make it in the device. Source. Okay. Change this contact name in device only. Okay. So I just delete this contact. Okay. Then source, activate this as, select this. Okay. Done. And now, if you are making any changes in the device, okay, whenever you are making any changes in the device, you have to build the mesh again because mesh.tdr file will change. I will deselect because I do not want to see the device again in the S visual. So deselect this. You just check the message here. Meshing successful. Okay. Now we can run this file. Okay, there is, let me just close everything and reopen it again. Build the mesh. So ac.cmd file, okay, same file, just close this. Okay, so now it is running. Okay, now it is, there is no problem. So first you can check the drain voltage is increasing from 0 to 1. So it reaches 1, it reached 1. Now gate will start increasing, gate voltage will start increasing. So drain is 1 constant. Now the gate voltage is increasing in the step of 0.025. So there are two 0.025. So let us check this. So it is increasing, right? So 0.35. So here it is increasing in the step of 0.025. Okay. So it reached 0.7577. Okay, so you can check here, drain voltage reached 1, gate voltage also reached the value 1. Okay, now you can open the S visual. So as I said, this is the AC analysis file. So in the AC analysis file, you will get the ID characteristics. First, let us plot the BGS characteristic. Okay, so I demo nmos AC dot, so design.plt file. Okay, there will be two PLT files. So design.plt file will have the ID BGS. I have to plot the gate voltage on the x-axis, drain voltage on the y-axis. So this, you can see I have not optimized the device, but the current levels you can check. Okay, at 1 volt, how much it is? 2.4 micrometer per microampere per micrometer. Okay, so what you can optimize the devices. Okay, different gate length, source length, channel length, and it is how, what is the length of the channel? So it is 120. Okay, so it is 180 nanometer technology node. Okay, roughly. So this is the ID BGS plot. Okay, now if you want to see the CV characteristics of the device, okay, delete the curve, open the second PLT file, that is nmos underscore AC dot design. So AC analysis, you will get the CV characteristics. So again, CV characteristics, x-axis on the x-axis, BG. Okay, gate voltage is on the x-axis. Now there are different capacitance values. Okay, so I just want to see the CGS. So where is, or CGD? Let us check CGD. So CGD on the y-axis. So you see, this is the CGD. Okay, CGD versus BGS. So this is the, you can plot CGS also. CGS. Select the CGS, plot this. This is the CGS plot. Okay, now if you want to extract the data, go to the data, export plot. Okay, select both the plots here, take it to the right side. Okay, export this file to the any name, you can give nmos underscore CV. F5 nmos underscore C. Where is this? Where it's saved? I just check it again. Desktop demo 1. It's already there. Where is the CSV file? Anybody can check? Yes, it is there. It is here. So there are two plots. So you will see first two columns. Okay, this is VG and this is the CGD. Okay, this is VG, different gate voltages, and this is CGS. And as I said, the step size is constant. So it is in the VG, the gate voltage is increasing in a step of 0.025. Okay, in a step of 0.025. So that is all about the MOSFET. Any questions on the MOSFET?
Sir, if we want, we can give body terminal also, right, sir?
Yes, yes. If you want to give, you can give the body terminal also, and you can connect this body terminal to the ground, or you can apply some positive or negative. If you want to see the body effect, okay, that is the body effect, right? So if you want to see the body effect, you just apply some voltage here, constant voltage, positive or negative, and you will see that ID will change. The threshold voltage of the device will change.
Okay, sir.
So here by default I am using that body is connected to the ground. Okay. Any other questions? Yes, students, any doubts? Okay. If no other questions, then whatever the device I have proposed in my research work, that is the tunnel FET, and that is the beyond CMOS technology. Okay, that is the beyond CMOS technology. So I'm not going in the detail of that device. I just directly show the structure and the IDVGS characteristics. Okay,
So everyone, hello.
yes, Hazar.
Yeah. So for the students, I'll just tell you, this is a research level work, which was one of the primary contributions of Dr. Ramakant's PhD thesis. So this part will be primarily useful for the students who are working in my research group. Okay. So they will be doing optimization based on the Gottfried devices. But as far as the other students are concerned, it will be an exercise, sort of a revision of whatever you have already learned. But the specifics of this Gottfrieds, why Gottfried, what are the advantages of Gottfried, those are kind of exploratory device, and it is still under lot of investigations, research investigations. Okay, so the students who are not in my research group, they can see this, how it is done. It is again roughly the same procedure as what Dr. Ramakant has been already sharing with you. However, for the students who are in my research group, they must look at this because this is the device which they're going to work in their RP. Okay. Thank you, Ramakant. Please continue.
Okay. So I just go to the N Gottfried. We have designed the N Gottfried and P Gottfried both, N type and P type. So again, open the terminal. To open the device, use the same command. So you can open the device also. Okay, so this is the dot set. Okay, dot set for the device structure. Okay, so you can change this. Let me just put the grid also. Okay, so this is 55 nanometer device. So you can check channel length. Okay, the effective channel length of the device is 40 nanometers. Okay, and so all the device dimensions. Okay, entered in the micrometers. Okay, 45 nanometer means 0.045 micrometer. Okay, by default, the unit of the sensors that is defined is in the micrometer. Okay, so if you are designing the device in the nanometer, you have to convert this nanometer into micrometer. So this 45 is 45 nanometer. Okay, that is 0.045 micrometer. Similarly, the thickness of this device is 12 nanometer. This is source region. This is drain region. If you see in the literature, interested students can go through the literature of the tunnel FET and MOSFET. You will find the device structure is almost same. Only the source and drain doping are different. Okay, so I just show you here. So this is the drain region. Okay, so drain is N type. Okay, so this is N type. Now if I see the source is P type. But what we have seen in the MOSFET, drain and source regions are same type. Okay, are doped with the same type of dopants. Okay, so that is the the primary difference between the MOSFET and TFET. Again, this is the double gate TFET. Okay, so okay, now I have hidden the meshing. Okay, so you can clearly see. So this is the channel, this is the channel, this is the source, and this is the drain. So here I am using different material. This is the silicon germanium, this is silicon, and this is also pure silicon, different type of dopants. Okay. Now here we are using this is the oxide. Okay. This is HFO2, then metal. Different metal is for N MOSFET, N type of device. Okay. The metal, the work function of the metal or the material that is giving the best characteristic is the aluminum, Al. Okay, you can see why the aluminum. Okay, so this is the device structure, and again we are using the double gate device. So similarly for back gate also, this is oxide and this is the metal. This is again the optimization of the device. We have optimized the device, so different type of oxide. So this is HFO2 and this is the oxide SiO2. Okay, there is different regions for using this just for optimizing the device. Okay. Now, if you want to see, you can create the mesh of this device. So designing steps, okay, designing steps are same. Whatever the steps I have discussed in previous two devices, you can use the same steps for designing any device, any 2D device, okay, any 2D device. Okay, now you can check this. So you can see the meshing is successful. So if you see compared to the previous two devices, here we have given very fine mesh of 1 nanometer. Okay, so this is one of the things that you can see that for this device, if you are increasing the meshing size, okay, the current will decrease, and optimum value of the meshing or the minimum meshing that we can use is 1 nanometer. Okay, again the doping profiles is seen here. Okay, so this is the device. Again, if you want to see the characteristics, IB characteristics or CV characteristics, the parameters are here. What is the difference between this CMD file and this CMD file? There is only one major difference, that is the backgate. Here I am using the backgate also. And here we have given the tunneling. Let me just tell you one more thing also, because MOSFET works on the principle of tunneling. Okay, so here in the physics section, we have defined the band-to-band tunneling generation also. What in MOSFET? Okay, if you remove this part also, in the MOSFET, that is the additional parameter that we have given. Okay, so if you remove in the MOSFET, if you remove this band-to-band tunneling also, there will not be any change in the IDBGS characteristics, because MOSFET does not work on the band-to-band tunneling. What here, if you remove this band-to-band tunneling generation, okay, you will get the current levels very less. Okay, their noise. Okay, so because the tunnel FET work on the principle of the MOSFET, so we have to include this model. Okay, these are the models. These are the different models that we are using in the simulation. Okay, so again, similar to that, first we will swap the drain voltage from 0 to 1. So where is the drain voltage? This. Okay, now here we are changing the drain voltage is here. Sorry, drain voltage is here. Here we are changing both the gates, front gate and back gate. Okay, we are using as a symmetric device. So we are changing the front gate, that is the BG, and back gate, that is VV. Okay, so we are changing the front gate and back gate, both the gate voltages from 0 to 1. So you can see here again, I have defined like this. Drain source, front gate is terminal G and back gate is terminal B. So we are changing the front gate and back gate voltages from 0 to 1. If you want to use this device as a single gate device, what you can do, do not change the voltage from do not change the voltage of back gate from 0 to 1. You can simply remove this line. Okay, that will be the single gate device. Okay, now if you want to see this, you can run this device again. So you will observe that this device simulation will take more time compared to the previous devices, because this is the optimized device, first thing. Second thing is we have used very fine mesh. Okay, so because of that it will be taking more time. So first drain voltage is changing. So drain voltage, you can change the drain voltage, because you can get the characteristics ID BGS at different values of BDS. Okay, so you change the voltage. So in the first two devices, I have used the drain voltage VDS equal to 1 volt. This is the ID BGS characteristics of the TFET at BDS is equal to 0.8 volt. Okay, if you want to see the ID BGS characteristics at different values of BDS, you can change this value of BDS. Okay, this I will explain when I will plot the ID BGS curve. Okay, so see, it is going very slow because this is the optimized parameters, optimized device, so it will take more time. Just wait. Now, so just whenever you are designing the device, right? Suppose you have designed a device structure. Sometime it may not converge also. Okay, it may not converge also. So it will not reach to the final value of BGS, that is 1 volt. Okay, so what you have to do? You have to either you can change your device structure, or you can make some changes in this CMD file. So there are two possible ways of converging the device. Okay, first is you can change the device structure or device parameters, and you can make some changes in the CMD file also. What the final value of the gate voltage should reach the 1 volt. It is not like that you design any device structure and you will get the IDBGS characteristics. No. Okay, that is the optimization part. Okay, so you have to select the, where is the device? I have removed it. You have to you have to optimize the doping parameters, then different type of materials that you are using. Suppose you are using the silicon germanium on the source side, right? Then how much percentage of the germanium you are using, that also you have to optimize. So you can read out our papers. We have how we have optimized the devices given in the papers. Okay, so you can see here now the gate, you can check gate and front, both voltages are increasing together. Okay, so you can see it is 0.54, it is 0.54. So now it is changing, it is 0.64, 0.64 volts. It will go up to 1 volt. So designing a device is not the difficult. Okay, what the optimization of the device. Okay, so whenever you are optimizing the device, many times this file will not converge. Okay, so that thing you have to keep it in your mind. So we can plot also. It is not necessary to wait till it reaches 1. Whatever value it is reached, it will give the IDBGS plot till that value. Okay, so I just open the terminal here and as visual. So what is the file name we have given? Final demo 1. Okay, so demo 1. So again, two files will be created. This AC dot file and the current design.plt. Okay, so current design.plt file will have the ID BGS characteristics. Okay, so let us first check. So front gate, you can take front gate or back gate on the x-axis. So I just take the front gate on the x-axis, drain current on the y-axis. So you can see it has been reached till 0.8. So you can check here also. It will reach 0.799. Okay, so that is 0.8. Now it will be increasing. So you can just press the reload button here or reload the file. Okay, so it will change. So just wait, it will reach till 1 volt. So just wait. See, now it is reached to 0.94. See, it is 0.9. Okay, so it is going towards 1 volt. Okay, now it has been converted. You can see here also. You will get the message here. Finished because curve trace the values. Okay, if it does not reaches the 1 volt, okay, it will display the error message here. Okay, it will display the error message here. So it is converted to 1 volt. Okay, now if you want to again, if you want to see the AC analysis, that file is this. Okay, so gate voltage on the x-axis, then CGD or CGS, you can plot different CGD. Let us plot CGD. So this is the optimized CGS. So you can see the CG is in the order of femtofarad at BGS equal to 1. And these are the ID BGS or CV characteristics at BDS equal to 0.8. Okay, if you want to see the CV characteristics at BDS equal to 1, what you have to do? You have to just change this value to 1. Just change this value to 1 and run this simulation again. Plot it here. Okay, you will get the corresponding plot of CV at BDS equal to 1. So that's all. Any questions now? Students, any queries?
Hello, hello, students. Do you have any questions? Okay. In that case, what I'll do is we can stop the recording here, and in case we will have probably a week's time or a couple of weeks' time, in which the students will have some time to basically have their logins created. They can essentially go through this example, this tutorial, this demonstration, and then thereafter, if they have any problems, then they are supposed to reach out to either myself or to Ramakant sir. And in the next session, if necessary, if you come up with the problems, then Ramakant sir, I will request Ramakant sir to give a second demonstration of around half an hour or so, if he has time and all that, where he will explain only your doubts. So since the students are not having any queries right now, so what I will assume is that whatever Ramakant has shown has been perfectly well understood as of now. And the second session, which I am telling, that we are going to conduct if and only if the students come up with any queries. Otherwise, I think Ramakant sir has better things to do. Okay. So Ramakant, is it all right?
So fine, sir. If the students have any queries, we will.
Yes.
Take
Because I mean, anyway, we already have some of these demos earlier. Ramakant sir himself gave a demo earlier. So this time it has been exhaustive, like 1.5 hours. So, and he has shown multiple devices also. So in case the students have any problems, only then we are going to conduct the next session on Centaurus TCAD. Okay.
So first get the login credential from the
Yes, yes.
VLSI level.
No, not only just the login credentials, sir. They should create the login credentials. They should work on it. And henceforth, we are going to ask only the results. We are not
Yes.
going to discuss anymore on how to do the device simulations and all that. Since we will assume that you have understood how it is to be done. So in short, me and Ramakant sir, we are not going to entertain any more requests how to run synopsys anymore. That's final. So if you have any queries regarding a particular step, or you are stuck in a particular step, then you should actually refer to this video recording. And if still you cannot understand or something, then we will essentially have a second session, but that is only going to last for half an hour or 45 minutes at the most, where Ramakant sir is only going to explain just the troubles or the places where you are going to have the problems. Okay, that's all for today. Thank you, Ramakant sir.
Just one more thing, that students, you can download the test underscore AC file and test underscore DC file from here. Okay, and this change it to .cmd files. Okay, you have to copy these files in your remote system and change it to .cmd files.
That txt should be changed to cmd.
Yes.
Okay, test underscore AC, test underscore DC, you can put your own name also, doesn't matter. Just the only thing is that you have to ensure that this particular test underscore AC and test underscore DC has to be run on the sdevice command. Okay, so sdevice will run, as Ramakant sir has already shown, sdevice space test underscore AC dot cmd.
File name underscore cmd. File
Yes,
name.
yes.
File name underscore cmd.
Okay, thank you, Ramakant sir. Ramakant sir has already done a fantastic job. He has uploaded the CMD files also. So I'll be stopping the recording right now. Yeah.
Okay, thank you. And we can log out now.
Yeah.